Okay, well, this is our final lecture for the dilution as an attenuation process sometimes. Today we're going to wrap up our talk about dilution as an M&A process. So Dave, can you give us a quick update from the last lecture?
Sure. Let's put this graphic up that we used in the last lecture. The way to visualize this is to have a vertical control plane perpendicular to your groundwater flow. And then you use the combination of the concentrations, the groundwater Darcy velocity, and the size of the plume. You get a mass discharge. That's a grams per day number. And mass discharge in this case, we're basically using that to describe the amount of loading.
That's right. And then our other term, mass flux, is the mass per time per area, such as grams per day per meter squared. Now, just a quick note that many earlier publications, the mass flux was used instead of mass discharge for this grams per day number. So you just have to be careful. But now the convention is that the loading is called mass discharge, and that this the most common units are grams per day, and this mass flux is this loading per area, basically, that goes on. So you can use this mass discharge as a first-order approximation of the impact, or it can be used for prioritization. And
maybe let's spend a little bit of time talking about how this prioritization works. There's a lot of variability in the mass discharge numbers from site to site, right?
That's right. So let's first talk about ohms, or orders of magnitude. These are these factors of 10. And I think the main message is that our business is an order of magnitude type business. And if you look on the left there, we have this plume, a plume map. And typically we draw them using orders of magnitude, like the outer contour is 1 microgram per liter, then 10 micrograms per liter, 100 and 1,000. They step up by factors of 10. And Dave, what's on the right-hand side?
Well, the bottom right, we've got basically hydraulic conductivity values. So these are a bunch of values. The source here in this case is the BioChlor manual, this modeling software. But basically describing that if we're talking about various types of geologic media, all the way from clays to gravels, you're talking about hydraulic conductivities in terms of these order of magnitude changes. So you might use terms such as like a 10 to the minus 3 sand, or 10 to the minus 6 clay. In this case, we're talking about the centimeters per second hydraulic conductivities. So a lot of times we're dealing with concentrations or hydraulic conductivity terms in these order of magnitude type terms.
Okay, and so that sort of, you know, sparks some thinking on our part, and then so let's expand our discussion and think about other natural phenomena that are based on this idea of orders of magnitude. So Dave, I'm going to give you a test here. I'm going to show you some pictures. Okay. Can you tell me what is the natural phenomenon and what is the scale that describes it? So let's go to the first one here. What do you see?
Well, this is earthquakes. This one I know. So we're dealing with the Richter scale here. It goes from 1 to 9. Every time you go up a unit, you're talking about an increase in damages by a factor of 10, right?
Orders of magnitude. Okay, so let's do this next one, next test. What is this phenomenon, and then what's the scale?
So these are photos of hurricanes or hurricane damage. And we use the Saffir-Simpson scale, right, to describe hurricanes or cyclones. You're going from Cat 1 to Cat 5. Basically, damage, again, is going up by an order of magnitude as you go up this category scale. And so I'm familiar with the pictures on the left. I believe that's Hurricane Ike and the damage associated with that. Not so familiar with the photos on the right, Chuck?
Well, I was personally impacted by Hurricane Ike. Actually, that's a picture of my, well, old car. That was the tree hit the chimney and it rolled down the roof and went right into my car. So I was part of that factors of 10 damage in that category 3 type storm. But the key point is that there are these natural sort of classification systems out there, Richter scale, Saffir-Simpson hurricane scale, that are based on these factors of 10 orders of magnitude. And so we said, can we do this for groundwater? And so we started out by taking all the sites that we knew, and this was using data that I helped compile along with Graham Carey from the ITRC report, and we put all of our sites together and came up with this table here. So here's, I think, about 40 sites, ranked from the highest site to the lowest site. And Dave, what do you see when you look at this mass discharge table?
Let me count what I'm seeing in terms of the orders of magnitude. But I think I'm getting up to 9 different orders of magnitude based just on the sites within these charts.
Going from 56,000 grams per day, which is our mega site, okay? And then this one over here, 0.0078 grams per day. That's the smallest one. What would we call that site?
Well, that would be the Pissant site, correct?
Exactly, okay. But then you see this scale here between the Pissant site and the mega site, 9 orders of magnitude. And so we said, hey, can we put these sites that are here, or any site, if you knew the mass discharge, into 10 different buckets? And well, let's see what we did here. So this is a paper we wrote with Dr. Shella Farhat. You were a co-author, Brian Looney. but we say that if you know your mass discharge, you can go into one of these buckets. And if you look right here, if you're greater than 100,000 grams per day, what are you classified as?
Mag 10 plume in this case.
Okay, and then a plume in the middle, 1 to 10 grams per day is a Mag 5 plume, and then this really small one, if you're less than 0.001 grams per day, a Mag 1 plume. So that's this idea that you can get this idea of what they were. So one other thing we asked ourselves is what was the sort of statistical distribution of this? So let's look at our 40 sites and see where they fall into this magnitude scale. And so we're looking at here, what's the X and Y axis here?
So we've got a plume magnitude category on your X axis here. So how many different sites then is shown on the Y axis. So we've got a sort of a distribution across from 1 to 9 in this case, of plume magnitude, and a few sites that fall into most of those different categories.
Yeah. Sort of looks like a bell curve, maybe a little bit.
You can
sort of see this distribution in here. But the idea is try to come up with this universal nomenclature, or this point of reference for people. You know, we can talk about earthquakes or hurricanes, but for groundwater hydrologists working on these plumes, it's like if you and I were at a bar somewhere and I said, you know, Dave, I just got asked to work on a Mag 7 plume. Now, what would you say?
Well, you know, I've been working on a Mag 8 plume myself.
Okay, and then we're there, and then somebody we don't know that's down at the end of the bar, she says, you guys are slackers. I'm working on 2 Mag 10 plumes. So.
Well, sounds like a pretty good bar, someplace I might want to hang out at.
Yeah, so if you had a bar with a groundwater focus, you know, maybe you could do things like instead of a martini, you would have a darsatini, right?
Where they play a lot of talking heads once in a lifetime, water flowing underground.
And then you get your ice in different sizes based on sieve size. So, yeah, this sounds like a pretty good bar.
Yeah, I think we can move on from that.
Okay. But the idea is if you have this classification system, you can also get information about potential impacts. And you can think about what's going to happen if that magnitude plume impacts a water supply well or does stream dilution. So if we look at this one here, and we have mass discharge on the left, and we could see what does it take to impact a domestic well that's pumping at about 600 liters per day. And it would take a Mag 2 plume to do that. And then a municipal well pumping at 400 liters per minute. That's about 100 gallons per minute.
In this case, it'd be a Mag 5 plume.
And then for the stream with a mixing zone flowing at 4 cubic meters per second.
Mag 8 plume in this case to impact that stream.
Okay. And so, so those are the examples of these different things about these different loadings that are out there.
So this sounds a lot like the TMDL concept.
That's right. So let's talk about that. An interesting point. I just have a slide about this. And there's in the surface water, this whole program called TMDLs, total maximum daily loads. And it's the amount of pollutant that a water body or a water segment can assimilate without exceeding their water quality standards. So here are some examples where they do some of these studies. What they really do is they say, here's the safe water quality criteria that we want to have for, in this case, copper or dioxin. And they figure out what loading won't exceed that level. So in the Copper River, it's 5,450 grams per day. And then there's dioxin in the Houston Ship Channel, about 0.04 grams per day.
So a lot of difference in these two different cases. I would like to point out that I do recognize one of the people in this picture on the right.
Oh, that's actually my wife, Dr. Hanadi Rafai, who runs a big TMDL program at the University of Houston in Galveston Bay. Looks like she's holding up one of those darsatinis at this bar we've been talking about, right?
You'd be willing to drink that.
Yeah, but she does a lot of work trying to calculate those loadings. So in some ways, we're talking about a concept that's very similar to this total maximum daily load idea that goes on in surface water. Okay.
All right, well, that's pretty neat stuff. I think we may want to take a little bit of a step back and address a few questions about mass flux and mass discharge in general, sort of covering the last 3 lectures that we've dealt with. So what's the big advantage to using mass flux or mass discharge concepts?
Good question. Just think about wastewater treatment plant discharges, from wastewater plants. What they want to know is the loading. The seminal capacity is based on these loadings. It's the mass per time and not just concentration. Concentration in some ways is just one dimension, one factor that you might understand, that you might need to know about to figure out the impact a contaminant may have.
Well, if you're worried about impacts, why don't you just measure the concentration in the well or in the surface water?
So you're talking about that Ironson McKay paper, and the idea was to use this formula, but they were using it more as a screening system for MTB plumes. They were saying, if this plume continues to migrate, could it cause a problem when it hit that water supply well or surface water? But if you had a plume that had already reached a water supply well, you wouldn't need to do that. The whole mass flux, mass discharge, you just measure that well.
Well, and then finally, I think for an M&A course that we're dealing with, is it really okay to consider dilution when talking about M&A?
I think it really depends on the program and the contaminant. You know, there's some ideas that the contaminant 1,4-dioxane has some pretty high aquatic levels. It's pretty safe in surface water relatively, but these other polyfluorinated substances, you know, they're not, right? They would be much lower. So you have to think of those type things. Some groundwater remediation experts have wondered why dilutions relied upon for wastewater and air discharges, but not groundwater. So it's an interesting question overall. Mm-hmm.
Well, maybe let's go over the key points then for this lecture.
Okay, first, mass discharge can be used as a prioritization system for plumes and as a tripwire to estimate if your plume is relatively strong or relatively weak.
And then secondly, dilution can be used as an M&A process, but really only under certain circumstances.